Welcome to the Mojave Desert. We're at an altitude of about 3,000 feet overlooking a wide, flat area. We're looking east and we can see mountains about 80 miles away, the Californian Aqueduct, and out there it's the Palmdale Airport and some peaks way in the distance. I've come up here to do some research. Let's have a look at Google Earth. I've drawn a line indicating the direction towards which I'll be taking a number of pictures to create a hyperlapse right at the aqueduct site. We're looking exactly east, and there's a few landmarks on the way. I'll be zooming in to a few of these peaks just to study them closely. Over in the distance, we'll see the Quartzite Mountain that I filmed before. One has to study all these peaks carefully because in infrared we can see so far and it's really hard to figure out what peaks we're seeing. So look at that. We're scrolling now towards the east, and we're approaching Quartzite Mountain right there to the right there. And I'll zoom in and you can see there's some antennas that we'll see in the photos. And right behind it, there's all these peaks out here, including this one particular one right there, which I've identified about 85 miles away. To create a hyperlapse, it's fairly easy. I walked down the hill and I took photos of the distant hills at periodic intervals going down a somewhat constant slope. And then in Photoshop, as you can see here, I layered all the images and I enabled visibility. And when I put that into a movie and speed it up, it's quite impressive. We get that sense that we're rotating the Earth, just like in Google Earth. But more importantly, interesting new phenomena become apparent. The hyperlapse was created by first aligning to the fixed points as shown. The green arrow points to the Quartzite Mountain, and that's the main alignment point. Now the foreground hills will bring the imagery in the background down. And so what I've done on the left, the two yellow arrows on the left point to additional alignment points that will anchor the image. So I rotated clockwise the imagery as those mountains were pulled down to exaggerate the pull down on the right side. So observe movement in the distant peaks on the right side. So as we toggle the scenery, the peaks on the left are fixed and the ones on the right drop down. You see that? Now let's zoom in. So now you can see it. Notice we need the grid to be able to see that the peaks are dropping down. Isn't that incredible, folks? Yeah, this is overlooking This is overlooking the Palmdale Airport towards the east from the aqueducts. Look at that. And this one as well. Now there's also distortions in the air. That's a given. So if I toggle between these two things, notice how there is some distortion in the air. You see that? Let me take the grid off. Look at that. Now the drop-down behavior is a combination of two phenomena. One is simply a geometric perspective, as you can see in this diagram. The features A and B lie along the same line of sight in this graphic, but if we change height, this is what happens. Now the two mountain peaks are separated in angle, and so on a photograph they would show vertically separated. Now a good question to ask is, what if point A was really close to B? What would happen then? In this case, the observer barely notices any change in vertical position of A relative to B when the two targets are at the same distance and far away. In my case, I changed height about 100 feet, and target A and B were at about 53 miles and 68 miles. So when we do the calculation, we realize that something else is going on. To understand image compression, have a look at this analysis. So notice there's two mountain peaks, the quartzite in the center at an elevation of 4,500 feet, and a mountain to the right about 4,900 feet at a distance of 68 miles. So it's farther back than the quartzite mountain. Now, the mountain should be about at the same vertical height as the quartzite mountain, but it's not. It's been compressed down. And when I say compression, it's relative to geometry, all right, and perspective. So something else, there's another phenomena that is acting on top of regular geometric perspective changes, and that's this compression, this image compression. So in the inset, you see I have an analysis of the angles to the distant mountain, and it's actually a delta in elevation. So my observation was from 3,200 feet, and so the delta is 1,700, and I calculate the angle, vertical angle, theta 1, and then I do the same thing for the quartzite mountain. And notice the angles are pretty close, off by 0.08 milliradians. And if you look at the picture, that whole mountain, the quartzite mountain, in the image works out to about 5.4 milliradians. The desert floor is at about 3,000 feet, and then you can do the math. So it is also, it should come out slightly higher than the quartzite mountain per the vertical analysis and the trigonometry, but it's way below, almost, I don't know, 2.5 milliradians down. So quite a drastic drop. So the geometric analysis does not explain the observed image compression. Something else is going on. And that's the exciting part, folks. That's the really exciting part. So what's really going on? Well, as you probably guessed it, there is some refraction that's occurring. But is it only atmospheric? Or is there something else? speed of light varies, as everyone knows. Sometimes there's temperature inversions and strange mirages appear. But the fundamental distortion which drives the speed of light is actually the curved space-time continuum that we're immersed in. And believe it or not, matter actually distorts this fabric of space. And everything is related. Light propagation and mass. So there is a bigger, deeper reality that I've been studying for quite some time. 30 years ago, I went to a gravitational anomaly location. I visited over 5 locations since then. And I will deal with that in my next video. This is just to whet your appetite, folks. Before I let you guys go, here's a view of some mountain ridges almost at 180 miles towards Mount Charleston in Nevada from the same location. Thanks for watching, everyone. Don't forget to subscribe, and I'll see you in my next video.